Problem 3, the energy can't squish since it's elastic. Yeah, like thermal energy is like what it would have become if it had lost some mechanical energy, because friction does that. All right, so question 3, finally some rotational motion, kind of. So, oh, someone asked me if I can post the work on the website. I can try. I'm not sure how that works yet. I'm not sure if like my work is actually explanatory enough to like do that. Oh, sorry. Wait. Read. A simple harmonic motion on the exam? I think so. I think other people would have answers for that. I'm not sure. Oh, right. You could watch the replay, but it's probably easier to like see the work itself. I don't know. Anyway, I'll just do it. Okay. So a simple pendulum of mass m and length L swings up to a maximum of 30 degrees before coming back down. Oh yeah, so you guys are already finding the period. No, I don't want you to find the period yet, but I mean, sure, if you want, you can find it. Aw. Okay, wait. Actually, like this is I want to correct. We'll wait till later. Conservation of energy for at least one of these. Yeah. Well, okay. No, stop. Stop predicting my questions. Oh, Walter Lewin is a really good lecturer. Yeah, I like. Yeah, this is a good recommendation. Like, I mean, the only one I watched is like his thing about what was it, like rainbows? I forget. Okay, let's move on to the question. So draw and label all the forces acting on the pendulum bob when the pendulum is at its highest point and when it's at its lowest point. So lowest, highest. So guys, help me out here. What is the free body diagram of this pendulum when it's at this point, the higher point? Just throw out forces. Tension, gravity, 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 gravity. Yeah, that's true. Like Walter Lewin has amazing dotted lines. I like highly recommend this. Okay, gravity, tension, T, M, G. Cool. Air resistance. No, there's no air resistance unless I tell you there is. Okay. So what about the lowest point? Why do we use T for tension when it also means period? Because science sucks. Also, we only have 26 letters in the alphabet, unless you count Greek letters. Actually, yeah, wait. Sucks. Oh yeah, that's true. Yeah, FT is like a good convention, but I usually use T personally just because lazy. Usually it's like clear from context. I don't think it's too easy to confuse them. Can't we just use scribbles? Dude, oh my gosh. I have a friend who like uses penguins to denote points sometimes. Exposing. Okay. So yes, we have solved this question satisfactorily. So move on to the next question. Let me erase this boy. Oh yeah, Chinese characters. Hey, it's actually like such a good idea. Okay. When the pendulum is at its highest point, this one, find the total torque acting on the bob around this point, the attachment point. So I call this the attachment point. And explain to me how you would find the torque. This is the positive direction over here. Have you not learned torque? No, I think people should torque. Non-physics. Oh, okay. Yeah, RF sine theta. MGL sine theta. What is theta? Theta is this, I think. Wait. Yeah. Okay. Well, okay, let's see. This is the way I understand torque. So torque is like how much, wait, someone raised their hand. Hello? Wait, person who raised your hand, what would you like to exclude? Like, what is your request? Yeah. Okay, so I'll just, like, what is your request? What is going on? I can just go ahead and continue. So, oh, okay, cool. Okay, so, what? Wait, where did that come from? Okay, so the way to think about torque is that torque is a measure of like force, but for turning motion, right? So you only care about the component of the force that actually would turn like the thing. So that's just this component of this force, right? So like that's why it's sine theta. Or alternatively, you can also think of it as like this force pulling on this lever arm over here. Like you can use this distance and this force. This like r. This is r sine theta. This is f. So like this requires some kind of like abstract thinking. Like this, there's no actual lever arm there, but it happens to work that if you do physics, you can pretend that it works like that, and the turning amount will be the same. Okay. Next, when the pendulum is at its lowest point, here, answer these conceptual questions. Is the total force acting on the bob? Oh, so this is the lowest point. And then the question is the total force zero? And is the total torque around this point zero? So let's answer the first question first. Is the force zero when it's at the bottom point? Wait. Okay. Yes, 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 yes. Such unanimous agreement. Yes. Okay. Well, I don't think so. And that is because there is acceleration at the bottom. Yeah, it's a pendulum. So, So which force is which force is bigger? Right? Like one of the forces, yeah, there's a net upwards force because so I misled all of you by not drawing the velocity vector at the bottom. This pendulum is moving. So that means there is a centripetal force. Or sorry, no. The net force has to be equal to mv squared over r, where v is the velocity. So like, I want to clarify the centripetal force is not a force, but like it's a way that we understand circular motion. So, oh, I'm sorry. Yeah. So the thing is like you don't have to actually find sorry, you don't actually have to find the force, but I just wanted to like explain that the force is not zero at the bottom. So like the variables we have are m and l, and theta is 30 degrees. So at the highest point. Okay. So yeah, centripetal force is not a force, but it is it's an idea that we use to help us with circular motion, because we know that if something is moving in a circle, then there must be an acceleration inwards of v squared over r. That's like the definition of that's like how circular motion works. So, but that doesn't mean that like there's a force called like centripetal force. Yeah, centrifugal force is also not a force in the lab frame. But I don't know if you know like about reference frames. So I don't know if that's the thing that people know about. Okay, so everyone agrees that the force is not zero. Any questions? So what about the torque? The torque around this point, is it zero? Who is this man? Yeah, sorry for not clarifying. For torque, yeah, R is L because the torque is half. So like the torque is the distance, like the torque depends on the distance from the center of torque and the force. So the distance here is L, or yeah, or R. Yeah, force has no perpendicular. Yes. So yeah, so the total torque around the attachment point when the ball is at the bottom is 0 because the net force is this way, and then that's going through the center of torque. So that's not producing any rotational motion about that center. So it's kind of like, you know, at a projectile. Wait, lies. No. What am I saying? It's like a simple harmonic oscillator. So like in the middle at the equilibrium point, it doesn't have a tendency to move in either direction. But when it moves away, it will come back. Any questions about this? All right. So now we place a pin at a distance of L/2 below the attachment point. The pendulum is caught on the pin for half of its journey. What is the new height to which the bob rises? I don't know if this is clear, but the bob is like the little thing on the bottom that moves. So, that's not how pins work. So I have a pin, let me draw an empty circle here. And then this pendulum will go like, woo. So what is this height above the bottom point? Why is this sound like an ethical Zenmei problem? I don't know if it is, honestly. I just wrote it. When you say still the same as what? This is the lowest point. All right. So yeah, this is just a conservation of energy problem again. So like when in doubt, use conservation of energy. Yeah, double pendulums are chaotic systems. This is a pretty interesting fact, but this is not a double pendulum because the pin, like I'm not sure if this was clear, but the pin is fixed to the wall. And so the pendulum, it'll go like this, and then the string will be bent by the pin, and it'll come back. And like, so there won't be like, this pin can't move, basically. We know, okay, thanks. Yeah, so this is conservation of energy. So the height is just the same as the maximum height of the pendulum without the pin. Questions? Right. Question E. When the pendulum hooked on the pin is at its highest point, which is this point, find the torque acting on the bob around the pin. So this is the center of torque. Oh yeah, you might not be able to find this like easily in terms of the equations, but I want like, so what is the torque? Like what are the forces acting on this bob? And then how does that translate to torque? Yep, T and gravity, right? So there's tension and there's gravity. Which of those is important for torque? Gravity, 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 gravity. And then, so how do you find the torque now? Like, you know, we only know that this height is the same and this distance is L over 2, right? Find the angle. Yeah, that's one way to do it. So how do you find the angle? Coordinate dash, trig, pretty much. So yeah, one way you could do it is, so if you want to find, you know, like R F sine theta, you would need to find this angle. And then in order to find this angle, you know, this over here is L over 2, and this distance right here is L over 2 minus H. So then you just dash. Yes. But another alternate way, which still involves trig a little bit kind of, is like, I like to think of it as that this force acts on a lever arm here. So this force, so we can just find this times this. And this you can just find using the Pythagorean theorem. Is theta always the angle between the string and the, this theta is different from the previous theta. I'm just like slapping on a variable here. Oh, you're saying like for torque? Yeah, like it depends on the situation. I mean, so like when we say like, this is why I don't like thinking of it as sine theta, because it gets confusing what theta is, I think. So let's say this is the center of torque, and then you have a force acting like here or something, or no, let's do a force acting here, right? And then this is the distance from the center of torque. That's like R or something. So torque is R times the component of F perpendicular to R, like this. R times, you can write it as R times F perpendicular, right? Or you can write it as R perpendicular. This is R perpendicular times F. Yeah, so like I like thinking of it like this, because then I don't get confused about the angles. All right, so I won't go through the calculation for that. Now, here's a big torque question. When the pendulum hooked on the pin is at its highest point, which is this point, consider the torque acting on the bob around this point, the attachment point. What is that torque? Like how it's, well, you can't calculate, this would be pretty hard to calculate explicitly, but like what are the forces that contribute to this torque? And how does this compare to the torque around this point? So what are the forces that are important again? Tension and gravity. Yes. Gravity, 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 gravity. Okay. So okay. So the torque due to gravity, how does the torque due to gravity around this point? Let's call it A actually. How does the torque due to gravity around A compare to the torque due to gravity around B? Which one's bigger? Same. C. It depends on L. The cross product. Oh my gosh. Okay, so it is, yeah, so they're actually the same. So, and the way I think about that, like again, we have, you can calculate torque by using F and R perpendicular to F. So then R perpendicular to F in this case is this distance. R perpendicular to F in this case is that distance. Those are the same distance. So they have this, the gravity does the same torque, right? So does that mean that the total torque is the same for both of these points? Is the total torque the same for both of these points? Clack. Okay, answer me please. Is the total torque the same for both of these points? The total torque acting on the bob. We've already determined that the torque due to gravity is the same, but well, let's say that, what if the torque was the same? Someone has raised their hand. Okay, actually ignore what I just said. So yeah, they're different. And the reason why is because before the tension was not important, but now the tension is important because it's not going through the center of torque. Yeah, exactly. Well, like the length of the tension is non-zero. Yeah. Yeah, so the tension actually has a non-zero torque and it pushes it the other way. So that like you can kind of imagine like taking this tension force and like using this lever arm here, and then whatever that is, I don't want to calculate it, but we know that this is negative torque, assuming that this direction is, oh sorry, what? No, this direction is positive torque actually, assuming that this is positive direction. Then the torque on this point was actually bigger than the torque here. And then for like, you know, for those of you who are familiar with angular momentum, this makes sense because when this bob reaches the bottom, the velocity is like some v, right? So the angular momentum of this ball around this point is less than it is around this point because the radius is bigger. And so that means and it makes sense because you need a bigger torque to produce a bigger angular momentum. Any questions? Okay. All right, there are just a couple of things left. We're almost there. So finally, what is the period you guys have already determined? Yeah, what is the period of the swing? But, yay, but there's a pin there. So what do you do? Yeah, what's the period for the whole swing? For a swing both the left and the right side. Yeah, the pin doesn't move. This is period. Yeah, I'm teaching your 8th period class. Welcome to my class. Fat guess. So yes, you do treat it as a shorter pendulum because essentially it's like hooked on the pin. So yeah, there's no like, the stuff up here is not important anymore. Yeah. So as people have said, the period of the regular pendulum without the pin is 2 pi root L over G. Let me confirm that. Yeah. So we take half of this, and then we take half of this short one, which is pi times root L over 2 over G. Oops, I need to make clear which one of those is bigger. 2 over G. Yeah. And so you guys know how to calculate this. I won't need to calculate this. Or actually, I guess you can just really quickly, it's like this times 1 plus 1 over root 2. But yeah, that's the idea. And now finally, oh, there's 2 more questions. My bad. Anyone have questions about this one? 1 over 2g. The 2 is inside the square root. So like the final answer would be something like pi times root L over G times 1 plus 1 over square root of 2. Any question? Counting the minutes. All right. 2 plus square root 2 over 2. Yeah. Okay. A mischievous, I learned how to pronounce that yesterday, elementary school student takes out the pin and flings the pendulum with all his might. That is, he gives the pendulum an initial velocity from its lowest point. What is the minimum initial velocity needed for the pendulum bob to reach the point, a distance L above the attachment point? Careful. So basically, yeah, just yeet that pendulum out of there. So it goes up, it needs to go all the way to the top of the circle, right? It is not a rigid rod. Yeah, it is a string. So what velocity do you need here? Yep, conservation of energy, yes. But the question is, what is the final energy of this state? Like, obviously the potential energy, mg2. Yep. Good. Okay, you guys know what you're doing. So yeah, in order to keep the bob moving in a circle, do we need to have, the net force needs to be equal exactly to the centripetal acceleration. Yeah, exactly. So the net force on this is mg plus tension, and we need this to be equal to mv squared over r. So then we can find, well, the minimum t is 0. So we want the minimum v at the top in order to have the minimum v at the bottom. So then we want the t to be 0 so that this is the smallest, as small as possible. So let's solve this. V equals, well, r here is L. Oops. Let me be nice and write that nicely. R is here is L. L, and oh my gosh. And so V equals what? Root GL. I think so? Yeah. So now we have a total energy up here of mg2L plus 1/2 mgl. Wait. Yes. Yeah. Someone check my work. Okay, I think we're good. Why are there 2 more slides? Well, okay, so does everyone affirm that I can probably figure out how to do the rest of this problem? Yes, I mean, so yeah, like you just said this is equal to 1/2 mv squared, whatever v is at the bottom. Yeah, and then you just solve that. So there is one more question left. And this one I probably will not solve out fully because it's actually like significantly harder. And I just wanted to do this to check in, what do people know about moment of inertia? So this question, why is it lagging so much? Frick. Yep, no more pin. But now we're repeating, oh shoot, go to the bottom. Yeah, I'm bullying all of you because now it's a sphere. And so, all right. So what is the change in approach for this problem? Like in general, what are you gonna have to do? We can use the same energy conservation thing, right? Kind of, but is it still valid? Yeah, exactly. Okay, you have to consider rotational kinetic energy. Yep. Well, the sphere is the same mass as the point mass. Yeah, so you have to consider rotational kinetic energy. And so I think the easiest way to do this is, like one of you said this already, is to consider the whole thing as one angular system. So this whole thing here you consider it all as having some moment of inertia around this center point. And you write like an X here. Yeah, like an X here. Yeah, so what is the moment of inertia of this around that point? You know what theorem you use to find the moment of inertia? Yeah, so the sphere, yeah, parallel axis. So the sphere is, it's a solid sphere, so it's 2/5. Wait, is that right? Isn't it 3/5? Wait, a solid sphere, 2/5. Okay, fine. Okay, 2/5 m r squared plus parallel axis m l squared. 4/10. Yeah. So, and then so you want to find now, like, you need to have some minimum velocity at the top. And so you just do the same thing, except now you're using the angular kinetic energy, which is 1/2 I omega squared. You have to find the minimum omega first, and then you do this, and then you're good. So I will not delay you any longer because, oh shoot, what is going on? Oh man, wait, what did I just do? Okay, so the last slide is this boy, because I want to thank all of you for coming to this class. And if any of you have more questions or clarification points that you would like to ask about, then feel free. This officially concludes the session. There's still 67 of you here, so thank you. Yeah, if you have any more questions, feel free. And also, I also have like a thing on my website, so you can put like a little message down there in the box. Show my website. Oh yeah. For I, we just add 1/2 I omega. Like you, instead of doing linear kinetic energy, you would do angular kinetic energy. So just like replace linear with angular, because that's the easiest. Well, for me, that's like the easiest way to consider it. I mean, it would also be valid to add like so you could do for the sphere a translational and kinetic and angular kinetic energy components, and have like translational plus angular plus equals translational plus angular plus potential. Does that make sense? But like, I think it's easier to consider the whole thing as a system, and then do that angular, just angular for that instead of angular and kinetic. Sorry, yeah. Let me give you my website URL really quickly. What does ML squared mean again for the attachment point? ML squared, that comes from the parallel axis theorem. Okay, bye-bye. So I think you can use the perpendicular axis theorem. This is my website. I can't scroll because the mouse is broken, but okay, well, I'll attempt to scroll using my stylus. So this is my website. You can see the options here. I will be posting this video on in this place slot thing, and then if you want to like fire me anything else, you can write a little comment in here. Okay, anything else that you want to ask about? Wait, hold up. Yeah, I cannot see. Slides, please. What is this class, and is it okay that you were talking? Yeah, I will be posting the slides too. Do I have? I'm not planning on doing one for AP Physics C. The APs are really soon, but I mean, if there's demand, I might do one. Like, I think that's worth it. Do I have an answer key for the slides? Not yet, but I can make one. Yeah, I cannot scroll. No. No, it's not what I want. Stop. There you go. What's the link to the recording? Well, I mean, the recording is still ongoing. Like I'll post it on my website in the part that says recording. Or it doesn't say recording right now, but it will. Thanks. Yeah, this, oh. Bye. How many people are still here? Curious. It's still 20 something. I'm just gonna chill and like doodle or something. Wait, how do I get rid of this? Like, do I teach? All right. Meeting officially adjourned. Oh, geez. All right. So throw any last words because I will be ending the meeting soon. Bye. Okay. Meeting official end. Goodbye. 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 Thanks for coming.